Hello everyone. It's our great pleasure to share with you our recent research on how to make deep reinforcement learning more industrially applicable. So reinforcement learning is drawing more and more attention from the industry. The scenario for reinforcement learning can be categorized by these three circles. In the inner circle, the environment is artificially designed and there is almost zero exploration risk. Games are exactly this kind of problem. The middle circle corresponds to the recommendation, advertisement, conversation, and other internet applications, where the environment is real, but the exploration risk is very low. And the outer circle corresponds to more industrial applications, including manufacturing, cloud computing, logistics, healthcare, so on and so forth. In these applications, interactions with the environment could be very costly, and sometimes bad explorations may even lead to disasters. It's clear that the addressable market is becoming larger and larger when we go from the inner circle to the outer circle. Therefore, it is very important for us to be technologically ready to learn a high-performance and reliable reinforcement learning agent for these industrial applications. Actually, besides high interaction cost, there are even more challenges for reinforcement learning in industrial environment. For example, because the environment is very complicated and sometimes not well defined, one can hardly build a simulator in an automatic manner. And it is non-trivial to smoothly transfer from the simulator to reality. Furthermore, the industrial applications usually have high state dimension and huge action space. In such a case, making globally optimal decision is highly difficult. To tackle these challenges, in the past few years, researchers at Microsoft Research Asia have conducted extensive research on continual offline RL, offline policy ranking, and distributed multi-agent reinforcement learning. And we have worked with several partners in the domains of logistics and supply chain to test the practical value of these technologies. In the remaining part of the talk, we will elaborate more on these technologies with their applications. So first, let's take a look at continual offline RL. When we say continual offline RL, we mean that the applications does not allow us to optimize the current policy by interacting with the environment directly. Instead, we will have to optimize the policy based on offline collected data. However, we have the chance to update our policy for multiple times, and every time we update the policy, it will be deployed and its interaction with the environment will be logged for future policy optimization. If we do this in an iterative manner, we will have a better strategy to continually optimize the policy and achieve better performance. When we say better performance, we mean at least two criteria: monotonic policy improvement and global convergence. Monotonic policy improvement means that every time we update the policy, its average performance in the real environment should be at least as good as the previous deployed policy. And the global convergence means that after many iterations of a continual offline RL, the eventual policy we obtain will be able to approach the optimal policy. Actually, the satisfaction of these two criteria is non-trivial. In our research, we proposed a mixed policy to trade off between them. The basic idea is as follows. First, we used the standard offline RL technology to train a pessimistic policy by giving zero reward to the explorations outside the offline data. Then we can also train an optimistic policy by giving carefully designed high reward to the explorations outside the data. Then when we conduct the next round of deployment, we use a linear combination of these two policies. We show that by carefully choosing the combination coefficient, we can obtain a good trade-off between monotonic policy improvement and global convergence. In particular, we prove that as long as the policy improvement is large enough, we can allow efficient explorations according to the optimistic policy without causing undesirable disasters. And furthermore, if the number of trajectory we collected at each iteration is large enough, even with finite number of iterations, the mixed policy will be able to converge to the globally optimal policy at the end. So in addition to the theoretical results, we also tested the effectiveness of the policy via experiments by comparing it with the standard offline RL algorithm. As you can see from the slide, the left figure shows the average total return. From the figure, we can see that our method is much better than the baseline. It is because it can more effectively leverage the internal connections between different iterations. And the figure on the right shows the state coverage with respect to different deployments. It is clear that our algorithm can explore the state space in a much faster and more comprehensive manner. When we introduce the framework of continual offline RL, there is actually one hidden topic which we haven't touched in depth. That is, how to determine whether the offline learn policy is indeed better than the previously deployed policy. This is usually referred to as policy evaluation. Ideally, we should run the policy in real-world systems and observe its behaviors in order to determine whether its performance is good or not. But unfortunately, this is not feasible, since a poor policy may seriously hurt the system performance and user experience. Therefore, we can only do offline evaluation. A widely used approach is to use the offline data generated by some other policies to evaluate the value of a given policy through importance sampling, as shown in this equation on the slide. However, this approach is biased with large variance. For example, the state generated by the given policy pi may not be well overlapped with the state generated by the reference policy pi b. In this situation, the estimated value will be biased. And furthermore, when p pi b is small and p pi is very large, this importance weight could be very large, resulting in a large variance in the value estimation. Given these challenges, we want to ask a question. Do we really need to estimate the value of a given policy? To answer this question, let's first revisit the common scenarios of offline policy evaluation. We have two typical scenarios. First, given a set of policies, which one is the best? And second, is a given offline policy better than the deployed policy online and could be able to replace it? We can see that no matter which scenario we are considering, what we need is to compare and rank different policies rather than accurately estimate the value of a given policy. With this in mind, let's check what kind of information we could leverage for this purpose. Actually, in many real scenarios, we have both the log data generated by previous policies and their true online performance. And this suggests that we can conduct supervised learning to rank the policies rather than unsupervised estimation of the value of the policy. So this is the overall framework for our proposed supervised policy ranking. The input of the system is a set of offline trajectory data D and a set of a training policy with true values. And the output is a scoring function which assigns a score to a policy based on the data D. And the criterion for learning is to ensure that the model could rank the policy in the training data as correctly as possible. Mathematically, we want to minimize this objective function in yellow. This slide shows the experimental results for our proposed offline policy ranking. As compared to several widely used offline policy evaluation methods, our model has a much higher rank correlation and a normalized absolute error with respect to the ground truth value, which is observed by testing the policy online. The result clearly shows that the advantage of modeling policy evaluation as a supervised ranking over the unsupervised value estimation is very clear. Having a good offline learning algorithm for RL is only part of the story. In order to really make reinforcement learning industrially applicable, we also need to deal with the scalability issue and other issues. Next, Jiangbian will introduce how we deal with this issue by using distributed multi-agent reinforcement learning, followed by a few examples of the applications of these technologies in logistics and supply chain.
Thanks, Tian. And let's then talk about how we leverage distributed multi-agent RL to deal with the scalability issue we have to face in many real industrial applications. To give you more sense about how the scalability issue, here we list the real problem scale in a few representative supply chain scenarios. They are all based on our engagement with Microsoft's customers in the industry of logistics and supply chain. For example, when we try to solve the container repositioning in ocean transportation, this optimization problem consists of thousands of ports and vessels in the whole shipping network. For another example, when facing the inventory management in retailing, the optimization problem involves tens of thousands, even millions SKUs, together with thousands stores or distributed centers. Such problem scale actually means high state dimension and a huge action space, which makes RL highly difficult to reach globally optimal decision. Therefore, we propose decomposing the complex global decision problem into decentralized decisions through multi-agent RL. However, to design industrially practical multi-agent RL, we have to face a couple of critical challenges in terms of both learning efficiency and systematic efficiency. Specifically, from the perspective of learning efficiency, we have to consider how to let multi-agent RL balance between model generalization and learning efficiency, and how to scale up the multi-agent RL under widely occurred competitive environment. And from the perspective of systematic efficiency, the challenge include how to efficiently manage massive experience data and how to avoid and balance the training workload in a distributed learning system. To address all these issues, we develop a distributed multi-agent RL framework, and this framework is built upon our open source platform Maro, which has been released for 1 year. And this framework is featured by 4 major components: the flexible policy mapping, contextualized training, hybrid experience management, and balanced task dispatching. They are all designed to address those learning and systematic efficiency issues. Let's first talk about flexible policy mapping. We know that if we let all homogeneous agents share the same policy, it requires the policy model with a large capacity to handle high variant data from multi-agent. It usually causes a low learning efficiency. And on the other hand, if we let each agent has its own policy, it is likely to result in overfitting for each agent. So to trade off between the learning efficiency and model generalization, we design an optimization-based method towards flexible agent policy mapping with the objective of both maximizing experience coherence for agents sharing the same policy and minimizing that between agents with different policies. This optimization method also introduces regularization on policy number and policy size variance. The contextualized training module is designed to ensure the learning efficiency of multi-agent RL under the competitive environment in which different agents may compete or share some contextual resource. Here, the contextual resources are indeed the basis of interactions between agents. To accelerate the learning efficiency for these interacting agents, we designed this contextualized training approach, which is essentially an iterative learning and a mutual reinforced process between policy training and dynamic context modeling. To further address the systematic efficiency issues, we first develop a hybrid experience management module that can efficiently handle the massive offline experience data by using an importance-based distributed experience rollout and a hybrid data storage. Besides a highly efficient experience data storage, they can also ensure sample efficiency as it leverages more data from agents with complex patterns. To avoid unbalanced training workload caused by unbalanced experience collections or variant model complexity in the distributed learning system, we further design a balanced task dispatching module. It can configure the training task priority based on its experience size and model complexity. Then it further ensures the balanced workload by designing flexible training ad hoc dispatching method with a general transparent interface. So far, we already have a good offline RL to reduce the interaction cost, as well as distributed multi-agent RL framework to handle the problem scale issues. In the following, I will use two example cases in logistic and supply chain domain to demonstrate how they can transform the industrial applications. The first case is container repositioning problem in ocean transportation, and this work is centered around our engagement with OOCL, a Hong Kong-based leading shipping company. And empty container in ocean transportation is the central resource. The trade imbalance leads to imbalanced supply and demand of empty containers in different ports. So there is a strong need to transport or reposition empty containers from the surplus area like North America to a deficit area like East Asia to mitigate the resource imbalance. This is typically an optimization task in the logistic industry with a couple of typical and vital challenges. First, the whole resource flow network usually consists of a large number of resource holders. And more importantly, there exists both cooperation and competition among them. It needs extra design to model such cooperation and competition. Meanwhile, the resource relocation environment could be quite dynamic in terms of both network connection and supply-demand distribution. Finally, the ultimate goal of this problem is also a trade-off between global-wise fulfillment rate and operational cost. These challenges can be naturally addressed by our continual offline RL with distributed multi-agent RL framework. Therefore, we define each port and vessel as agents, and the policy is to determine the number of containers to transport once a vessel arrives at a port. And we integrate the continual offline RL and offline policy ranking algorithms with the distributed multi-agent RL framework to form up the whole RL-based solution as shown by this figure. Experimental results on a sub-shipping network between Australia and East Asia show that our method can achieve more than 1,000 times speed up in the online decision making and reduce the terminal cost by over 10%. Moreover, the learned policy is very robust when a significant percentage of the ports are unavailable due to unexpected reasons. Currently, more than 50% ports operated by OOCL have been leveraged the output of our learned policy. In fact, this RL solution can be leveraged to solve general resource repositioning tasks whose goal is to distribute a pool of resource to different nodes to fulfill their dynamic demands. And such resource repositioning tasks are widely occurred in logistics and supply domain. Another case is the inventory management task in the supply chain industry. In general, the task is to deliver the right good to the right place at the right time for maximizing revenue while minimizing cost. So here we define the agent as stores as well as each type of SKU, and we should learn the policy that is to determine the procurement timing, amount, and the supplier for each SKU. As a typical optimization task in supply chain, it faces similar critical challenges. First, there are a large number of SKUs flowing with complex connections between supplier, warehouse, and retailing stores. Moreover, there exists both cooperation and competition as different SKU may compete for a warehouse shared store spaces, while warehouse and stores should cooperate with each other to satisfy potential customers' demand and SKUs. And the inventory management environment is also quite dynamic since there exists a dynamic service level, price of suppliers, variant fulfillment capacity, and emerging business events. Finally, the ultimate goal of this problem is also a trade-off between global-wise sales and operational cost. Similarly, we built up the RL-based solution by integrating continual offline RL, offline policy ranking into the distributed multi-agent RL algorithms. Experimental results on open data from Walmart show that our method can achieve over 100 times speed up in online decision making, reduce the terminal cost by over 10%. More importantly, the learn policy is more robust when facing more severe competition conditions, such as highly limited warehouse capacities. So this RL solution can also be leveraged to solve a general resource flow management task whose goal is to maintain an efficient flow of goods or materials among a supply chain network, particularly when demand and supply are fluctuant. This is also a widely occurred and one of the most important tasks in the supply chain domain. So a quick wrap up with some future outlook. Along with our steps from an inner circle to the outer, we have conducted extensive research on continual offline RL, offline policy ranking, and distributed multi-agent RL to address the challenges in terms of interaction cost and the problem scale. Through working with several partners in the domain of logistics and supply chain, we have verified the practical value of this research work. In future, towards higher performance and more reliable RL agents for broader industrial domains, we believe it is crucial to continue the deep research into the directions, including how to increase sample efficiency, how to improve model generalization and scalability, and how to build up general services to lower the entry barrier for broader AI consumers. So that's all of my talk. Thanks.